Hey guys, this is the follow-up to my first video about kind of the chapter 1 introductory stuff. So if you want more practice problems, you're in the right place. I will be going over bond line structures, identifying how many carbons and hydrogens are in a bond line structure, formal charge, again, number of hydrogens, drawing out bond line structures from Lewis structures, and determining whether or not something has a formal charge. So that's what we'll be doing in today's video. Again, this is chapter 1 of organic chemistry. Most of this chapter is an overview of your general chemistry, so atomic orbitals, geometry, whether something is linear or trigonal planar, but I will be focusing on just kind of the organic chemistry aspect. So let's get started. This first problem, and feel free to pause it if you ever need more time. That's why I made this in the form of a YouTube video, so you can work on it with me. So if I'm going too fast, just pause it and you can catch up with me. But this first problem asks, for each of the following molecules, count the number of hydrogen atoms connected to each carbon atom. The first problem has already been solved for me, and the numbers indicate how many hydrogen atoms are connected to each carbon. So main thing here, count the number of hydrogen atoms. So in order to do that, we need to determine how many carbons we have in a molecule. So let's focus on 1.14 here. We have an aromatic structure, so one that goes in a circle, kind of like this. Let's count up these carbons. So one thing that might throw you guys off here is we have a double bond going to what seems like nothing. Now don't worry, remember that even if there's nothing there, there's either a carbon or hydrogen there. All right, we know it can't be a hydrogen. And why do we know that? Why? Ask yourself why we know it can't be a hydrogen. I'll give you a few seconds. Because for all these molecules, there's no, formal charge indicated. So if this was double bonded to a hydrogen, that would fill hydrogen's octet. Hydrogens only want one bond connected to it. So we know it's not a hydrogen, so it has to be a carbon out there. And let's label all these other carbons. If you want more information about bond line structures, I highly recommend you guys watch that first video that I made. But this has 1, 2, 3, 4, 5, 6, 7 carbons. Remember that at each little zigzag or corner, whatever you might call it, that indicates a new carbon. So we got 7 carbons. This carbon has a double bond, which I'll show right here. This is what this is. So for this carbon at the end, if it has 2 bonds right here, it needs 2 other bonds. So 2 other hydrogens have to be at the end of this. So let me erase that and show these 2 hydrogens to make it 4 bonds. Remember, it has to be 4 bonds for each of these carbons because there's no formal charges attached to this compound. So we need to make 4 bonds for each carbon. This carbon right here doesn't need any hydrogens. It already has 4 bonds. It has 1, 2, 3, 4. So no hydrogens for that one. And the rest of these are going to be 2 hydrogens. And why do we know that? Because the rest of these are single bonded to 2 other distinct carbons. So we have, for this one right here, we have 1, 2 bonds. So to make it a filled octet, we need 2 other hydrogens. So you can do that for each one of these. Okay. And counting these up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. All right. Pretty simple, pretty simple. Again, for this next one, 1.15, we have a triple bond. This one is called a terminal alkyne, which means that it's at the end of it. So this has to be another carbon at the end because it can't be a hydrogen. Hydrogen only likes 1 bond, and we have 3 right here. So it has to be a carbon at the end triple bonded to another carbon. We have yet another carbon that starts this chain of carbons right here. So I don't want you guys to think that there's no carbon right here and it just starts off with more carbons from this triple bond. You have to have another carbon right there. Okay, and that's often a mistake, is not thinking that there's a carbon right there. So we have 1, 2, 3, 4, 5 carbons. Let's count out how many hydrogens we have. All right, so we have 3 bonds. We need 4, so that means there's 1 other hydrogen connected to that terminal carbon. This carbon has a triple bond, so it has 3 on the left side and it has 1 on the right side. So this has 0 carbons. We don't have to write anything there. And the rest of these, let's see how many they have. We have this carbon, which has a single bond, and another single bond. It has 3 bonds, so it only needs 1 hydrogen. And these two both are connected to 2 bonds, so they need 2 hydrogens. All right, counting these up, we have 1, 2, 3, 4, 5, 6 hydrogens. Pretty straightforward. Let's skip these two because I think we're good on hydrocarbon chains. So let's focus on one that has a oxygen. All right, so we have this 1.19. All right, let's focus on this one. So we have a carbon right here that's double bonded to this oxygen, and we have 2 carbons at the end. All right. This carbon in the middle has a double bond and 2 single bonds, so it has 4 bonds in total, so that has no hydrogens. These 2 at the end, though, only have a 1 single bond, and there's no formal charge, so don't think that, oh my gosh, there's only 1 bond connected to another molecule here. No, there's 3 other hydrogens at the end to make it 4 bonds connected to each of these carbons at the end. So in total, we have, let's see, 1, 2, 3, 4, 5, 6 hydrogens. All right, hopefully that makes sense. Again, just keep track of how many bonds they should have for these carbons. And when you get into more complex structures with oxygens and carbons and hydrogens and nitrogens and halogens, it's really important to understand how many valence electrons and how many bonds all of these should have. And it looks like I didn't go through this one. So let's go through this structure right here. This looks very different than what you guys have probably seen before. But we can think about it in the same way. This is called a confirmation of something that you've seen. So you've seen structures that look like these bond line structures. This is just another depiction of a bond line structure. So we can think about it the same way. So this, let's write in these lone pairs for this oxygen and see why it doesn't have a plus or negative formal charge. It has 1, 2 bonds, so it has 2 sets of lone pairs. Oxygen likes to have 2 bonds, so that's why it doesn't have a formal charge attached to it. So we're good there. All right, we're focused on carbons and hydrogen, so let me write in all these carbons. Remember, these are bonds. Even though they're shown in kind of a 3D fashion, those are still bonds. You can see the zigzag pattern here, where there's corners at the end and there's a little bit of zigzag in the middle. If you want some tips on drawing this in the future, all you have to do is draw a zigzag here, draw the 2 corners, draw it in like this, and finish it off. Obviously, you could erase this top and put the oxygen right there, but that's a simple way to draw these kind of structures. All right, let's focus on these hydrogens. So this carbon has 1, 2, 3 bonds. So this carbon has 1 hydrogen. These 2 carbons at the end only have 2 bonds, so they have 2 hydrogens to make up for it. This carbon again, has 1, 2, 3 bonds. So it has 1 hydrogen. And it's a symmetrical structure, which means that these, whoops, forgot to fill in the rest of my hydrogens, which means that these two at the end are the exact same number of hydrogens as these two at the end here. Symmetrical structure. All right. So counting up all the hydrogens, and I don't want you guys to get confused with this line thinking that it's connected to this carbon. It's not. So let's count up all these hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. All right, that's enough counting. Let's focus on assessing the formal charges. So this is it's not part A, part B, part C. This is just a multiple choice problem. So let's try to eliminate some of our options. This asks, the following structure has been drawn without formal charges. Which statement describes the missing formal charges? So let's go through all of these atoms in our molecule and determine if it has its octet fold, if it's exceeding our octet, if it's not meeting our octet rule. Let's see. So let's start with hydrogens because those are the easiest. It looks like all of our hydrogens have 1 bond connected to each other, so those wouldn't be displaying any formal charges. So feel free to X those out if you're doing this at home. Those hydrogens don't have any formal charges, so let's focus on the rest of our molecules. This nitrogen right here, we know that nitrogen likes to have 3 bonds to fill its octet. Oxygen likes to have 2 bonds to fill its octet. So this nitrogen looks like it has 1, 2, 3, 4 bonds instead of the 3. So this one is exceeding its octet. Now, if you know that this is a plus on the nitrogen, feel free to put that plus right there. If you still have to calculate the formal charge, that is totally fine. Again, the formal charge, you can watch my previous video, is the number of valence electrons minus the number of dots plus the number of bonds to calculate the formal charge. So we know that nitrogen has 5 valence electrons. It has, let's see how many dots are hidden here. 2 dots, and it looks like it has 4 bonds. So that is 5 minus 6. Did I do that right? I don't think I did that right. I think there's 0 dots actually, because if there's 4 bonds, it wouldn't have any dots there. So that's 5 minus 4. That gives us a +1 formal charge. Kind of mistaken myself there, because if it has 3 bonds, it has 2 dots. So if it has 4 bonds, it has 0 dots. Okay. So this would be a plus for the nitrogen. So we can cross out this D right here. The structure has no formal charges because that nitrogen has a plus, and we can cross out this C right here because the C says there's no there's no positive charges, and that nitrogen has a positive charge. So let's keep going because we still have A and B to get through. Next atom we should look at is this carbon. Carbon likes to have 4 bonds, as we just saw with this latest practice problem. And let's see if it has 4 bonds. So it looks like it does, so we don't have to focus on that one. Let's look at the next carbon. Does that have 4 bonds? We have 1, 2, 3, 4. It looks like it does, so both those carbons are good, no formal charges. These 2 oxygens differ though, and if you know right away that oxygen likes to have 2 bonds to fill its octet, then you know that this one has to be a formal charge. This oxygen has 2 bonds, that oxygen is good. This one only has 1 bond, so let's calculate that formal charge if you don't already know that it's a -1. So oxygen has 6 valence electrons minus, let's see, 1, 2, 3, 4, 5, 6 dots plus 1 bond. That's 6 minus 7. is a -1 formal charge. So going back to our multiple choice, we should have one positive and one negative formal charge, so A. B was one positive and no negatives, but we know that oxygen has a negative formal charge. Okay. This question asks, in a multiple choice format, how many hydrogen atoms are in the compound represented by the following bond line drawing? Okay. So let's see, we have one already. So we know that we have one hydrogen. Let's try to figure out the rest. So as we did before, we know that this is a carbon at the end. We know that these, filling out the rest of the carbons, we have 3 carbons connected to an alcohol group. All right. This carbon right here looks like it has 2 bonds, which means it needs to have 2 other hydrogens to make sure it has 4 bonds attached to it. This carbon right here has 3 bonds, so it needs 1 hydrogen to make sure it has 4 bonds. And this one needs 2 hydrogens because it's attached to a double bond only, so it needs 2 other hydrogens to compensate for it. So we have 1 from our alcohol right here. We have 2, 3, 4, 5, 6 hydrogens in total. All right. One way you can mess up on this is not counting this hydrogen. I bet many of you would say 5 if you weren't counting that. But remember, even though that hydrogen is connected to an oxygen, that is still a bond that isn't shown. So that bond could be shown as something like that, but it's shown as this, which that oxygen has no formal charge because that is a bond right here. So that would be 2 bonds. As that bond from that carbon, that's 1 bond, and that bond from that hydrogen. Okay. Last one here is converting between Lewis structures to bond line structures, which is really important in organic chemistry, to go from these Lewis structures to thinking about zigzag format and double bonds, triple bonds, and just lines and bond lines. So for this first one, it kind of looks like a tree. This is like the roots of the tree. This is kind of the branches. So let's go to a bond line structure. So bond lines are, again, these kind of structures, which are in zigzag formats and only show kind of those lines, no carbon or no hydrogens unless they're connected to oxygens or nitrogens or halogens. You don't show those hydrogens if they're connected to carbons. So for this first one, let's look at this chain right here and let's draw that out. What would that look like? We know it wants to be in zigzag format. It wouldn't look something like this. Let me just draw a straight line. It wouldn't look something like this because they have an orientation about them. We know that those are sp3 carbons because they're all attached to single bonds. We know it wants to be in zigzag format. So let's draw our carbons like that. So carbon 1 would be the one right there. Let's say this is 2 and 3. That would be 2. That would be 3. Okay. On carbon 2, so we labeled this carbon 2, it has 2 other branches to it. And we know we can't draw those 2 branches as something like that, because if you watch in my other video, these bonds want to be as far away as possible. And again, you don't want to draw it as this either, because this is sterically hindered. Those bonds are pretty close together. So you want to draw it something like this. Okay. That second carbon that we labeled has 2 other carbons attached out from it. Those carbons all have 3 hydrogens attached, and we have accounted for everything there. And your final structure should look something like this. Okay. Using that information, we can think about This one right here, we have a 3-carbon, let's call it 4-carbon chain. Nope, let's call it 5-carbon chain that we can draw it here. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons, which show the 5 carbons right here. Let me erase those numbers. Let's keep them for the time being. We see that on carbon, we labeled it carbon 4. We have an oxygen that is double bonded. Again, watching my latest video, you don't want to draw that double bonded oxygen like that because that's too close to the other structures. So let's draw that double bonded oxygen a little neater like that on carbon 4. Then on carbon, let's say 5, we have 2 branching out structures. Let's call those 6 and 7. You can draw those as just another part of the zigzag, so we can say that's 6. And on carbon 5, we need 7. That's attached to carbon 5 still. So these are pretty far apart that you can draw, and they account for all the carbons we have here. So hopefully that makes sense, what I did there. Remember, it's just zigzag format. So remembering and labeling, if it helps to label all these carbons as I did 1, 2, 3, 4, 5, 6, and remember that that 7 was initially attached to that 5, so you have to show that in a bond line structure. All right, this next one is something different. It is a cyclic compound, so it goes around in a cyclic fashion. So let's draw this differently. There is no kind of zigzag here because it goes in kind of a circle. That's why I call it cyclic. So let's draw that oxygen at the start. We know that it has 2 bonds connected out. And those are those 2 carbons right here. This carbon kind of goes down here. They start to go down. So let's draw that as well. And then these 2 carbons at the end, let's call them, let's say 3 and 4, connect right there. So we have 1, 2, 3, 4 represent 1, 2, 3, 4. So we have our carbons in the cyclic compound. We just need 2 CH3 groups going out from carbon 2. So let's draw those as well. All right. So final structure without the labeling. Something like that. Okay. This next one, we have halogens. So we have some bromines in here. Let's do the original zigzag format. So this accounts for our 3 carbons. If I want to label them 1, 2, and 3, this is 1, 2, and 3. On carbon 1, we have a bromine. Let's keep that zigzag format. So that bromine's going up like that. And on carbon 3, we have a bromine as well that can go up in our zigzag as well. This accounts for all of our hydrogens, all of our bromines, all of our carbons. So that is the final answer there. Last problem set I have here is read as, for each of the structures below, determine if the oxygen or nitrogen atom has a formal charge. If there's a formal charge, draw the formal charge. All right, it's helpful to know, again, that oxygen has 2 bonds to Phillips octet. Nitrogen has 3 bonds. So we can kind of get through these pretty quickly. Determine if there's 2 or 3 bonds on the oxygen and nitrogen respectively, and we can go from there. So for this one, there's no formal charge. It has those 2 bonds that's connected to that oxygen. This oxygen has 1, 2, 3 bonds. So it has 1 more bond than it wants. That's going to be a +1 formal charge. Nitrogen wants 3 bonds. It looks like there's only 2 on this nitrogen though. And if it needs another bond to fill its octet, it's going to be a -1 formal charge. If you want to go back and calculate the formal charge, we have 5 valence electrons minus 4 dots plus 2 bonds. That's 5 minus 6. That's a -1 formal charge. This nitrogen looks good. It has 1, 2, 3 bonds connected to it. That looks good. This nitrogen has 1, 2, 3, 4 bonds connected to it, although. So that's going to be a +1 formal charge. This oxygen looks like it only has 1 bond. It needs 2, so if it needs another bond, it's going to be a -1 formal charge. This oxygen, kind of in the opposite matter, has 1 more than it needs. It needs 2, and it has 1, 2, 3 bonds. It's going to be a +1 formal charge. And don't write your formal charges as +1. Just write it as a plus, and don't write it as a -1. Write it as a negative. Okay. This last practice problem, we have a nitrogen that has 2 bonds. So it needs another more to satisfy its octet rule. So it's going to be a -1 formal charge. All right, thank you guys for watching this video. My next video will be about resident structures. So how can you change these structures with their formal charges to make resident structures? And feel free to subscribe and like if you like these videos. I'll see you guys in the next one.